So for the next exercise, we will take a look at PerlinNoise, and I'm going to base the kind of theoretical aspects of this exercise on the book The Nature of Code by Daniel Schiffman. So Daniel Schiffman is quite well known in terms of creative coding, particularly for processing, and the nature of code is all targeting processing, although there's a openFrameworks port of the exercises. But I'm mostly concerned with the kind of theoretical approach of generative media coding or generative coding from his book. And Daniel Schiffman will probably discuss this more in class, but Daniel Schiffman presents different ways to kind of create generative behaviors, one of them being random walks, and the other being probability, distribution, normal distribution of numbers, and we're going to skip all that. It's quite simplistic. Custom distributions of random numbers, so this is a bit what we've been doing to a certain degree, using a lot of random numbers. But I want to take a look at PerlinNoise for this exercise, and I want to discuss a little bit how to get out of this idea of randomness. So, for example, in our previous exercises of particle systems, you had the particles kind of going different speeds and going different directions. In the previous one, we also had a kind of a random distribution of squares in the screen. And random is very useful, but it's like static noise on a TV screen to a certain degree, because it's all over the place, right? So no matter how frequently you retrieve a random number, you always get the current number is always unrelated to the previous number. But with PerlinNoise, that's not the fact. That's not the case. So with PerlinNoise, there's a little bit more organic evolution of values over time. And that's really useful for computer graphics, namely to reproduce naturalistic textures, terrains, marble-like textures, and things like that are more organic in detail, right? And in openFrameworks, we have a method called ofNoise that allows to access PerlinNoise. So PerlinNoise is named after Ken Perlin, and he's kind of a multi-awarded kind of researcher, and even recognized by the Oscar Academy, because he worked, for example, he developed PerlinNoise when he was working for the Tron movie in the 80s, the original one, of course, to create these kind of naturalistic textures back then. So that's PerlinNoise allow us to kind of access a curve of values. Instead of trying to obtain random values all the time, we can access this curve. And we can access this curve through the dimension of time. So you have a dimension of values, and you also have a dimension of time. So you can get points in time which are close together, and they'll be smoother the more you jump in time to retrieve the next value, the more rougher the transition, or the faster the transition it will be, and to the extreme that it will look like this. It will look like the random graph. So there's a figure here that Daniel Schiffman presents that is quite elucidative. So if you go in small steps of 0.01, for example, in time, you get very smooth values. If you go 0.1 in time, it can go quite a big jump. So probably we want to have smaller jumps in time rather than larger jumps in time, right? So let's get to it. Let's create, I'm going to open Project Generator. Here we go, Project Generator. And we're going to start with a simple example, which is 1D, and in the next exercise, we'll do an exercise in 2D using X and Y. So I'm going to point to my folder, which is Generative Media Coding, open. And I'm going to call this exercise exercise 6, PerlinNoise1D. Okay. So we're going to generate, and I'm going to open in IDE, right? So, okay, now, what we're going to do, we're just going to try to use only draw. For this simple exercise, I want to demonstrate a circle moving on the screen from left to right using Perlin noise instead of random. So I can exemplify with random, and then we can go to Perlin noise. So Perlin noise always gives us back a number between 0 and 1. You cannot define a range like you do with random. You'll have to map it then to the range that you want to use. Okay, so let's do it with random first, and then we will use the Perlin noise. So if we have a circle being drawn, so we're going to draw it here, of draw circle, and the position x should be random, so I'm going to create here a float pos x equals of random, and this random will be between 0. Well, we could actually use of random height, right, or of random width. So that could be even more useful. And then of draw circle, which could be pos x, a random position, and in the middle of the screen, for example, so of get height divided by 2, and then radius of 50, similar to what we used in the previous exercise. Since we're dealing with circles, I might as well set circle resolution of set circle resolution of 100, for example. Okay. So if we play, as you will guess, this will be quite jittery, right? So let's take a look at that. Whenever it runs, there you go. So you have very jittery, very jumpy kind of circle being drawn, right? So what if we want this movement to be smoother, right? Of course, we could create a velocity like we did last exercise and have it move, etc. But we are trying to get it from the onset a good noise number, good generative number that we could use. So instead of doing it this way, I'm going to comment out. We're going to use of noise. So I'm just going to show you in openFrameworks in the documentation where we have that of noise. Here we go. We're going to use noise just as a float. So it's this example here, calculates a one-dimensional Perlin noise value between 0 and 1. So whatever numbers you put here on of noise, that is going to be kind of the seed to calculate the noise value. So let's go back to Xcode. So let's type it in. float pause x equals of noise, and here as a float we can put a number, but that if we put any number, if we put a fixed number, this will not animate the circle. So this will create a value between 0 and 1, which we then need to map to we need to scale this to the width of the screen. So actually we could just multiply it by of get width, right? Because here we get 0, between 0 and 1, and if you multiply it by get width, we scale it to the width. It's pretty easy to do it this way. If you want, we could also use the of_map function to map pause x, which is between 0 and 1 to 0 to of get width. But I find that this is simple enough that we don't need to use of_map. So now if we run it, we will have a static circle, because we are looking in a time value. So 10 is a time value, and the value is always the same. So we need to make that 10, instead of being a 10, a kind of a continuous value, and a continuous value that changes in time at a certain speed that is useful for us. How do we do that? So we need a float to calculate time here. So for this purpose, I use a lot, we've used in the past to calculate time of get frame num. I quite like to use as well of get elapsed time. So of get elapsed time, and you can get elapsed time in seconds, which is of get elapsed time f. It's a float. Seconds as a float. So this is really useful because it's not an integer. You get actually the decimal points of the seconds. You can get it as milliseconds, but then it's a really big number. And as you see, we need small numbers for this time series in PerlinNoise. So I find that this of get elapsed time f is pretty useful. So let's do that. Of get elapsed time. And then, sorry, I should have put the time before the pause x, right? And we add the time here to the noise calculation. So my fear is that this might be too jittery. If it's too jittery, we need to scale, to have also a multiplier here and make it smaller, this number a little bit smaller. But let's see how we get along with this value. It's out of the box. It's already much more organic than a random number, right? We don't even need to scale it. It works really, really well, I find. So this is it. This is kind of a simple PerlinNoise example, and we can now tweak a little bit the time. We can make the time go a bit slower, but what's happening here is that we are traveling in the curve. We are traveling in the curve of values at a certain speed. The speed is actually the real speed in seconds of what's going on. We can, if we go to Xcode and we can make time be of a slower evolution by, for example, if we divide this by 10, or it's the same as multiplying it by 0.1. So 0.1 is now my time scale. And I'm slowing down the reading of the Perlin noise by 1/10. So what we have is a slower moving circle, right? And if we divide by 100, we have a faster moving circle. And reversely, if we multiply by 2, it's going to be twice as fast. Right? And if you multiply too much, then it becomes like random because you're just jumping. If I multiply it by 100, it's almost like a random number because we will be making really big jumps. You see, not quite like a random number, but almost, because we're jumping, we're traveling in the time series, in the PerlinNoise time series, too much, okay, in too big a jump. So it becomes, and that's not. It's not for this type of results. Let me get back. It's not for this type of results that we use PerlinNoise. It's more for the kind of smooth results of this type that use PerlinNoise. So there's a lot out there on the web about PerlinNoise, and it's really useful. There's an interesting video I'll probably show you in class. There's a video by Daniel Schiffman where he explains precisely this that he explains as well in the book. So I'll leave you the link in the My Courses website. And this is just a starting point for PerlinNoise. So in the next exercise, we're going to see a bit more interesting application of this. This is just an introduction so that we kind of understand what PerlinNoise is.